Jim, thank you for joining us.
Thanks for having me. And I am overwhelmed by such a great crowd. Thank you all for having me.
Yes.
He was like, I didn't expect this many people. I was like, this is like 20% of the people who applied.
Yes, it is. And you have like, what, 150,000 followers on Twitter?
Something like that.
You're a little well known in the community, so we're just very lucky to have you here.
Thanks.
All right, so I gave a quick bio, but that doesn't really do justice to all you've done. So I want to start out by just laying the foundation and just, could you walk us through the arc of your career so far?
Yes, so I will start with the story of my career because I think it ties together nicely today's topics and also many of the kind of historic milestones in AI. And that also provides some perspective on how I got here today and doing what I'm doing right now. Steve Jobs said, right, like we can only connect the dots looking backwards. So we cannot connect dots looking forward. Mm-hmm. And now kind of looking backward, at my 10 years of history in AI, I think there are just many kind of magical moments I want to share with you. And also, just to sum it up, I think I was like super lucky because many times I just happened to be at the right place at the right time. And typically not by choice, but not by design, but just because of randomness of fate. So I started my undergraduate in Columbia University in 2012. And 2012 was the first year of deep learning. So AlexNet was dropping in 2012. Mm-hmm. And I was among kind of the first crowd reading that paper. And I still remember the excitement because before AlexNet, right, computer vision was this giant pipeline, super messy pipeline. You have a lot of features and statistical methods. And AlexNet came and just blew everything out of the waters because it's a single neural network that maps pixels directly to the output. And that's it. And you train it on lots and lots of data. So that was a very inspiring moment for me. And I was like, I need to study AI, machine learning, neural networks in particular. And then I joined an undergrad research group at Columbia University. And my task was speech recognition. But back then, deep learning wasn't a conventional wisdom. So the way they did speech recognition was you do things like phoneme classification. Many of you haven't heard about phoneme, and that's exactly my point, right? It's such a weird thing. And then you do phoneme classification and you do some sequence models that are like old school, classical programming stuff. And then you go through a very hairy pipeline. So I wasn't impressed by that, but I think that was still, my first kind of serious research effort, but it wasn't elegant enough. And then I heard that Andrew Ng went to Baidu to be the chief scientist. So in the summer of 2015, I applied to Baidu's internship at Sunnyvale. Actually, the Sunnyvale office was kind of open for Andrew Ng's group. And he was building a system called deep speech. So you can tell from this name, right? Like deep speech is a neural network. And Andrew's idea was, let's get rid of all the phonemes, all the linguistic stuff and the old stuff. Let's just have one neural network that maps from raw audio wave to the sentence, to the spoken sentence. And that's it. And we will just scale it on a lot of data. And then at that time, I was assigned, again, not by my choice, but I was assigned to an intern mentor called Dario Amodei. And that name might ring a bell. He's now the Anthropic's CEO. And back then, for that summer, I worked very closely with Dario. And we did like pair programming together. So Dario was talking about something called scaling up. And he was like, we gotta have, like our neural networks are not deep enough, are not big enough. We just need deeper and fatter neural networks. So to be very honest with the audience, I did not recognize the significance of it. I wasn't completely buying into this scaling up story. I was skeptical. I wasn't against it, but I was skeptical. And Dario pushed for just making bigger and deeper neural networks. And back then, it was 2015. There was no transformer. It was like recurrent neural network, some older methods. But even for those methods, you can scale it up. You can throw in more parameters. So that was kind of my first exposure to like industrial deep learning system and scaling up. And then Dario left Baidu. And in the summer of 2016, he said, Jim, like we are starting a new company It's going to be exciting. And we had a great summer last summer at Baidu. So do you want to join me in this new effort? And I'm like, hell yeah, Dario, like wherever you go, I will follow. And that company is called OpenAI. So Dario co-founded OpenAI with people like Andrei Karpathy, Ilya Sutskever. And back then, OpenAI was quite a magical place. Basically, if you look at their list of staff, staff of their technical team, these are all big names, the biggest names you can see in machine learning. So for example, Andrei Karpathy was there, Ian Geffellow, who invented GAN, Dirk Kimmer, who invented the Atom Optimizer, which basically every neural network relies on, Jonathan Ho, who later was the co-inventor of diffusion models, and Peter Beal and John Schulman, who's the inventor of PPO. They were all there in the summer of 2016. And I was like literally the dumbest person in the room at that time. There were like 35 of them, around that number. So my internship project in 2016 was one of OpenAI's earliest attempt at AGI. OpenAI has always been talking about AGI way back in 2016. And that project is called OpenAI Universe. So the idea is simple. We want to train one AI agent that can read the pixels on a computer screen and then control the keyboard and mouse, right? If you think about it, this is the most general interface you can have for an agent, because basically everything that we do in a digital space, be it writing emails, playing games, browsing the web, using Photoshop, using any software, can be expressed in reading pixels and then generating actions in keyboard and mouse. It sounds very appealing. And that was a huge initiative that OpenAI started. And the part I was responsible for, and by the way, at that time, my intern mentor was Andrei Karpathy. And Andrei and myself, and then later Tim from Stanford, we were responsible for a part of it called World of Bits. And that's a great name started by Andrei. Andrei's great at naming things. So the World of Bits project was part of OpenAI Universe, and that was to control the web browser specifically, reading pixels from the web browser and control keyboard and mouse to do tasks on the web, like browsing Expedia, searching for information, playing some simple web-based games, and so on and so forth. So that was an early attempt at my internship project, but it ultimately didn't quite work out because there was no transformer, there were no foundation models back then, and we only use reinforcement learning, and there's no hope that reinforcement learning in this vastly complex space can generalize to anything zero shot. It's just really hard. So OpenAI Universe didn't quite work out. And then I left OpenAI after the summer, and I started my PhD at Stanford with Professor Fei-Fei Li. So for Fei-Fei, many of you might know her as the inventor of ImageNet, which ties back to 2012. ImageNet was what made AlexNet possible, because neural networks need a lot of data to train. And before ImageNet, it were all like small data sets, and ImageNet had 1.2 million images, and huge by that era's standard. And I joined Fei-Fei's lab again at a pretty good timing, because the field of computer vision is seeing a transition. If we think about AlexNet, right? AlexNet was one of the first successful computer vision neural networks. If you think about it, it is taking like a static snapshot, a screenshot of the world, and telling you the objects in it, like be it cat or dog or truck or airplane. And it's kind of weird because the human vision systems doesn't quite work that way. We are embodied. We're living in this 3D physical world, and we perceive a constant continuous stream of pixels. We don't learn by seeing a bag of unrelated images, which is how AlexNet was trained. So at that time, at Fei-Fei's group, embodied agent is becoming a theme, where we want to have not just computer vision, but embodied computer vision. Having a visual system that's embodied in the physical world that can take actions, observe the consequences of the actions, and use that as a signal to improve itself even more. And it's all like video and just a constant stream of pixels coming in. That's how we, as humans, develop our visual system. So during that time, the term kind of the embodied agent, this idea was planted in me. And also in addition to AI agent at OpenAI, which is also the OpenAI Universe was another agent in the digital space. Right? Yeah, and then in 2018, I happened to host Stanford AI Salon. So they rotate hosts every time. And Stanford AI Salon is this interesting event. It's a weekly event on Friday. Basically, there are a group of people, and then they invite some really big name guests, and no electronics allowed, no phones allowed. Everybody will just have like a closed door discussion. And I happened to be the host of that particular event where they invited Pedro Domingos and another guy in leather jackets. And he's Jensen Huang. So Jensen and Pedro came to Stanford, and I was their host. And it turns out that they don't need hosts. They're basically self-hosting. Like Jensen is almost like a stand-up comedian. He's like so good and he's so charismatic. And so was Pedro Domingos. And they had this discussion. I'm like, okay, you guys are, just go ahead. You know, you're making my job very easy.
You got this.
You got this, you got this. And afterwards, I talked to Jensen. I told him about embodied agents and stuff. He was very excited by this. He said, like AI agents, you know, robotics will be the future. And you should do your life's work at NVIDIA Research. So I did an internship there in 2020. And then after graduating in 2021, I joined NVIDIA Research. And I've stayed there ever since. So now I'm a senior AI scientist. I've been there for 2 years. And then just one more milestone before we move on. And then last year at the NeurIPS conference, I was presenting MineDojo. And then there was another milestone moment in AI, and that is meeting Kanjun and Josh. And you know, back then it was still generally intelligent, right? And you guys were presenting the Avalon work, and I was amazed by it. We were in the same panel together because MineDojo and Avalon share a lot of kind of common ideas and philosophies, but also differ in different ways. We had very interesting and very unique design choices. And yeah, we can get into that, but that's basically a quick overview of my history.
Super interesting. All of these moments. Something I'm curious about is you're really into embodied agents. And I think at this point, that's actually a controversial view. And so I'm curious, what is it about embodiment that still compels you? I think a lot of people building agents in the audience today are like, oh, we can use language models or maybe multimodal models, and that's like enough for getting agents to work. What are you interested in? Why?
Yes. So I think large language models and multimodal models will be kind of a key piece to the puzzle, but they are not enough. I think embodiment is not just useful, right? Because we can use embodied agents to do robotics, and we can discuss about kind of implications of the applications. They're not just useful, but I think they're on the critical path towards unlocking high levels of intelligence. Because if we think about it, again, just like AlexNet, language models learn in a very peculiar way and very unhuman-like, very alien way, right? How does language model work? How are they trained? Lots and lots of internet data. You scrape and then you kind of brute force by predicting the next word. But think about how human babies learn. When you were born, you were not stuffed in front of a computer screen and then reading 1 million Wikipedia pages as your first class, right? You don't do that. The first things that human babies do are like using their hands, feet, and air and mouth, and just experiment, right? Interact with objects, experiment, listen, see, basically immersed in this world, in this 3D world, and then do experiments in it, right? Trial and error, and understand physics in this process. So there was a saying that all the babies are scientists in the crib. And I really like this saying because I feel that is kind of the next step in the evolution of LLMs, is to give it embodiment so that its knowledge is no longer castle in the air and abstract and only exists from reading statistics on Wikipedia, but it's grounded. It makes its knowledge executable by taking actions in this physical world, observing the feedback, and learn from that. And in this way, in this loop, you understand causality. You understand what we call intuitive physics, right? Like if I spill this bottle of water, my brain cannot compute the exact trajectory of every water molecule. But I roughly know that it's gonna spill in this direction and it's gonna make a mess and make both hosts angry. I kind of know that, right? These are what we call intuitive physics. And I think partially the reason why LLMs hallucinate is because they're ungrounded. They don't have this embodiment. They don't have the experience that we have, so they don't know what is impossible. They basically just compute statistics because they don't have the life experience that we have. And I think that at least partially explains, why they hallucinate so much, saying things that are obviously wrong to us that are against the common sense. So yeah, embodiment is the key.
When you say embodied agents, just to be clear, what do you mean by that? What is embodiment?
I mean, agents that can control a body and then interact with a world. And now that world does not have to be physical. It could be like virtual embodied agents. In Minecraft, for example, that is an embodied agent. In Avalon, a simulation, that is an embodied agent. Basically in like a 3D kind of immersive reality, and the agent can control a body.
So not to get too into the details, but a devil's advocate might say something like, okay, acting on the internet like World of Bits counts as embodiment because I can act on the browser and run experiments. Maybe one thing I'm curious about is with language models, maybe they don't experiment. I mean, it's kind of hard to prompt them to experiment like a scientist would because of the way that they're trained and the next token prediction. And so maybe the issue of like why it is that language models are not scientists is not embodiment, but rather some kind of objective function that like would result in this kind of experimentation exploration behavior. Do you think embodiment is necessary for that behavior?
I think there are some weak forms of being able to explore and exploit, kind of just using text. But I feel that having embodiment is maybe just a faster way to do it. Because if there's
and you mean like literally any action, being able to take actions is a faster way to do it, basically.
I think yes, taking actions is the key word. Yeah, but one thing about embodiment is you get this multi-sensory feedback. So you can, in addition to kind of training textual reasoning, you also get like pixels and audios. And instead of training multimodal models like static snapshots and you take a bunch of images and they're kind of captioning text, you do it in this embodied world. I think at least for computer vision, I wouldn't say this about reasoning necessarily. I think for reasoning, you may get away with just reading lots of Wikipedia. But for vision, I think that is definitely the most effective way.
Yeah,
is through embodiment.
It's a tricky thing because like computers are serial in a way that humans are not. And like in reasoning is serial, and that's why we can get away with reasoning in language. But I agree that like dealing with this multimodal input in a serial environment, I don't know how to do that yet.
Yeah. And there's also another argument is when you are embodied in a world that is rich enough and open-ended enough, and if the agent is able to explore very well and keep its kind of curiosity, then you basically get infinite data, right? Data is the bottleneck for today's foundation models. And we have all heard about that. Oh, like OpenAI is running out of tokens, right? We all heard about that because basically like all these kind of big foundation model creators, they scrape the internet and we're kind of exhausting the useful tokens and the high quality tokens on the internet. There are just so many of them that you can publicly scrape, right? But interacting with the embodied world produces infinite tokens. It is like a constant stream of experience and you make your own experience. And you will not only have infinite tokens, but you also have very high quality ones because you control what kind of tokens you want to get. That's what we mean by kind of scientists in the crib, right? Like babies take actions in things that they are most curious about. And now think about what's curiosity. You are only curious when you don't or you cannot predict the outcome of a certain thing. Like if I am so certain about my daily routine, I'm no longer curious about, is brushing teeth, gonna bring me a lot of curiosity today? Is that like a wondrous moment, washing my face? No, because you know exactly what's gonna happen after brushing your teeth or, washing your face. But if you're going into some events or I don't know, concerts or going to like Burning Man for the first time, you're curious. You have never experienced that. You cannot predict what's gonna happen. Much like when I walk in this event, right? I did not predict there's a huge crowd here. Now I'm getting curious why people are interested, right? Because it's hard to predict. And that is where curiosity is. And if you do something like curiosity-driven exploration, basically you're taking actions to gather the information that's most useful given your current mental state. And that is an extremely effective way to learn.
I want to transition a little bit to use cases. So once we have these embodied agents, what are you most excited about the use cases that it makes possible?
Yeah, I love this question. I've been talking about philosophy, but now it's time to ground ourselves a bit in like actually economically useful things. Love it. So I think of AI agents applications divided into 3 areas. One is software. And I think, yeah, Kanjun can speak more to this. You're building AI agents like around this space. And gaming is a second major application. And robotics. Basically, robotics are AI agents in the physical world. So let's talk about software. OpenAI Universe was one of the first attempts at doing this, right? Having this digital agent. But using kind of reinforcement learning wasn't the right approach. And I do think today's large models solve many of the problems that OpenAI Universe couldn't solve back in 2016. Now you get code generation, you can execute those actions, but they're still not quite robust enough to actually do like, especially for like high stake tasks, they're still not robust enough. And the reasoning is still not strong enough sometimes. And also the alignment, right? Like, are they exactly doing what you want? So I think these are some of the problems that better language models will be able to address. Do you have a comment, Kenji?
I was going to ask, what were the problems you saw in World of Bits that you feel like are actually solved today? And then what are the remaining unsolved things like, for the founders building agents in the audience?
So I think what language models have enabled are like zero-shot behaviors. And that is critical for building anything that needs to generalize, right? To kind of in the wild queries, basically. Your customer comes in and they can literally do anything. And you want the model to adapt to anything, at least reasonably. Now, I think the rest of the things I mentioned are all kind of not solved, but at least we're making progress, like safety, robustness, safety in terms of if you are giving it code execution capability, that safety becomes a big issue, right? You need guarantees that it wouldn't accidentally delete your database. You need to have guardrails around it. And these guardrails may not necessarily be a neural network. They could be like some more kind of enforced by traditional software, but we need to rethink the whole stack around LLMs. Now, there's one analogy that I really like, and I borrow from WndrCo himself, is that LLMs are operating systems. I just love this analogy. I think it works super well in this application of LLM for AI agents, is that LLMs are operating systems. And why are they operating systems? They have a very new interface, and the interface is language. And you can install software in the form of tools, of tool use. And OpenAI, ChatGPT App Store is a perfect example of LLMs using tools, right? It has hard disk in terms of vector databases. Now, instead of saving explicit things, you save embeddings and later you retrieve, right? There's hard disk. And there's also different file types coming. And these are multimodal language models. You have images, text, audio, 3D, multimodal is coming. And these are like correspond to different file types. And you also get the downsides of operating systems that are security. Now you get virus, right? Like Windows has virus, and the virus for LLMs are, prompt hacking, right? All those, really kind of weird and funny prompt hacking we saw on Twitter. Like these are the new type of virus. And there are also defenses against them. There is a very active research field like adversarial, prompt defense. And that is an emerging field that I wouldn't even think would happen if you asked me 5 years ago. Just what the hell is adversarial prompt? It's like, doesn't make any sense. But now it makes total sense because of this new operating system, right? So, and the thing is, right now it's very early in LLM as operating system because you can think of it as a single-threaded computer that's only maybe 10 hertz, right? It's generating 10 tokens per second. So it's kind of ridiculously slow and not parallelizable. But I think this analogy is gonna go a very long way in the future.
I'm really curious. So there are a lot of founders in the audience building agents. If you were an investor and I came and pitched you, hey, I'm a founder building agents, what would you be skeptical of? Like, where you think, these problems are not gonna be solved for 5 years. Like you shouldn't be building a company around that.
Yeah, I think it's easy to build a demo these days. It's like exceptionally easy to build a cool demo, exceptionally hard to make a robust product, right? Like demo, you just cherry pick one of those prompts, and then you run it a couple of times until it produces some cool stuff, and then you show it on Twitter and get a lot of attention. But it's really hard to build this robustly for all the use cases and customers. So I think the question I would ask is how robustly it's working for in the wild uses, right? Not just the ones that you think your customer will use, but the use cases that customers actually are entering into the prompt box, right? Like what are they typing? And that's one thing. And the other thing is about long tail, right? There are many kind of customers come in with specific needs, and it's very much case by case. And we know that LLMs are good at addressing kind of the like the mainstream use case, some of the most common ones. But for the long tails, they kind of falter. So how do we address those problems? Maybe using retrieval. There are like many methods around it. But I think those are the questions that one should pay attention to.
Are there methods that you think are most promising for robustness? I kind of think of it as like, we invented error correction at some point, or like we invented TCP/IP to deal with robustness issues in circuits and wired channels. What are the abstractions here?
One is retrieval. So if you're able to kind of retrieve data and do citations, that will definitely make LLMs more factual and hallucinate less. And the other is just having like a software stack around LLMs, right? If you give LLM a code interpreter, then you may very well make this code interpreter secure, so it doesn't delete your database accidentally. You need to have a custom interpreter just for the LLM, right? So you're kind of developing a specialized program for this new operating system. So I think like all of these things need to be rethink from the ground up.
I want to take a step back, and we're going to have to go into questions soon. You, unlike many researchers, you're very out there, especially very much on Twitter. That is surprising. That is not, you have quite the following, much bigger following than most. I'm curious, how did that happen? How did you become outspoken and amass this huge following? And also, has it changed anything for you in your career?
Yeah, so I like to share ideas. And I think since ChatGPT, right, hit the shelf and there was an explosion in the interest of AI, and I was suddenly stunned. So I've always been working in AI, and when ChatGPT came, I also tried it out. I was impressed for sure, but not like I did not foresee the earthquake that ChatGPT resulted in. And then there's a lot of noise in the community, right? Kind of cool demos and overclaims, just lots and lots of them. So I do want to kind of help the community increase the signal to noise ratio. And I get a lot of fun and pleasure doing this, right? Kind of cutting through the noise and trying to also put my perspective, not just sharing papers, sharing methods, but also putting my personal perspective on it. And it isn't always correct. I've always been updating my own belief as well, right? But I think this process is a learning process for myself as well.
And has being outspoken, getting a lot of feedback, having a lot of people see what you have to say, has that changed anything for you? How you look at this world, your career path, anything like that?
That's the reason why I'm here today.
That's true.
Thank you so much. Thanks,
yes.
Twitter.
Totally.
I don't think that's the reason you're here. The reason you're here, I think, is Voyager is really interesting. So Voyager, which Jim built, is an agent that builds its own tools in order to solve Minecraft. And I think one thing that's really interesting, well, I won't tell you what's interesting about it, but you're really interested in gaming. What do you think is the most compelling thing to do next in gaming if you were to do something in gaming today over the next 5 years?
I absolutely love this question. So I mentioned 3 applications of AI agents, gaming and robotics. I will quickly kind of gloss over how I think of these 2 industries. So first about gaming. Gaming is like the whole industry is absolutely insanely enormous. Mm-hmm. Actually, gaming in terms of market cap is bigger than the entire Hollywood and the entire music industries combined. That's how big gaming is. It is literally the top 1 biggest sector in the entertainment industry, and by far the biggest one. So huge economic value there. Now, where I think gaming is going, the kind of after doing Voyager, by the way, Voyager is like AI. So we have an AI to play Minecraft, and it's able to play this game play Minecraft for like hours on end and kind of discover new things all by itself. So that's a quick recap of what Voyager does. So after Voyager, I realized that that's where gaming is going. We have intelligent NPCs in open-ended worlds. And every time you talk to them, they not just kind of reply as in textual-based chat, but also reply in actions. Like your interaction with those NPCs affect their future and their mental states and how they act in the game. And if you propagate this effect exponentially, given you have like many NPCs in the game, you can imagine a world where games become truly alive. Something like Ready Player One. I just want to see Ready Player One becoming a reality. And I actually think that's going to happen in the next 3 to 5 years. Well, maybe not the fully embodied part because that's like AR and VR, but just about the intelligent NPCs and a world where there are so many AIs interacting with each other. And every time you open a game, even though it's the same software, you have a different experience. Every game becomes infinitely replayable and personalized. And every time you play it, it's a unique experience. Just think about the engagements, right? This type of game will draw and the emergent behaviors it will produce. So the other day I was talking to my friend and he was playing Elden Ring. Elden Ring was a big title. And it's a beautiful game, right? It's open world, just so many NPCs, so many kind of different things you can do and lots of Easter eggs, right? It's crazy the amount of work that the team put into Elden Ring. But you still get bored after maybe 2 weeks. For some people, maybe 2 months. But eventually you get bored because you exhausted all the NPCs, you beat all the boss, and you go back, like you already killed the boss, and they respond, and they still say, I'm gonna kick your ass. But, right? They don't remember that you've already interacted with it. The game is dead. But just imagine if you have NPCs, intelligent NPCs in games like Elden Ring, or Minecraft, or Legend of Zelda, that adapts every time, that has long-term memory, that maybe they remember you betrayed them once, and now it's their opportunity to betray you. Just think about kind of how complex these games will be, right? And the other research work that I want to highlight is a work from Stanford called the Stanford Smallville, where they instantiate 25 agents in like a little world and have them kind of interact with each other in the simulation. And the agents don't know they're in a simulation. So it's kind of like a digital West world. The agents interact and they go to work together. And 2 of them, I remember even fell in love, planning like a Valentine's party, right? It's a very inspiring research. And I think that's where the whole field of gaming will move towards. But the thing about that particular paper is because it's based on ChatGPT, ChatGPT is way too polite. So it's not that fun to watch. Like there are families in it, and there's like a father and a son, and the son is, "Morning, how are you doing, father?" And the father says, "Great, how are you doing, son?" "I'm doing okay, thank you so much for asking." That's what ChatGPT does.
All right.
We'll do better, and we need to do better.
We need to do better. On that note, first round of applause for Jim. Thank you so much for sharing.
Thanks.
And now we'll move over into Q&A. So one question came, what new tools or abstractions will AI engineers need that don't exist yet?
I think there are really good kind of new tools enabled by LLMs, like LangChain, Llama Index, all of these like open source tools, and vector databases as well, right? Let's still go back to this OS analogy because I think this question ties very nicely to it. Like, what does an OS need, right? It needs kind of software. It needs APIs to interact with the core computing engine. It also needs like better disk. So maybe there are kind of more things to be done on the vector database and retrieval. And also multimodal is coming. And I think having like pixels, having images and videos will also enable some new tools, maybe new interfaces around them. So some open source libraries on AI native UIs may also be very useful.
Got it. Siobhan Single, someone here. Can you grab back left?
What do you think about reinforcement learning as a good problem framing for AI agents today and embodied agents in moving forward? You mentioned Pedro Domingos as well. He's notably been critical of RL. So I'm curious, like pros and cons, any nuances there?
Okay, that's a great question. So the question is about what's the role of reinforcement learning in kind of embodied agents, and are they going to be useful into the future? So reinforcement learning is already very useful in language models in terms of reinforcement learning from human feedback, ROHF. Right? Reinforcement learning is this way to align the LLMs towards what a human intention is. So it's already useful. And in terms of embodied agents, I think reinforcement learning and LLMs are two powerful tools doing separate things. And it's best framed in system 1 versus system 2 thinking. So it's from the book Thinking Fast and Slow. Basically, system 1 is like high level, deliberate planning, reasoning. And system 2 is kind of rapid, automatic. Basically, the things you do that you don't even think about consciously in your brain, like how am I controlling each motor in my hand to hold up this bottle? How do I kind of cook breakfast or brush my teeth? These are actually very complex motions, but you don't allocate compute in your brain to these. So these are like system 2. I think LLM is awesome for system 1. They're deliberate. You can do reasoning, chain of thought, all of these, and high-level planning. But reinforcement learning will be very useful for the low-level controls. Because for many of the, as I mentioned, like how you control a hand, you can express that in language, right? Like how exactly am I controlling my hand to grasp objects? I cannot express that in language, but it's done by reinforcement learning, trial and error. And that is the best way to train these kind of dexterous controllers. So in robotics, I think this kind of combination of LLM and reinforcement learning will be the future, where you have high-level planning done by a language model and all these low-level skills learned by reinforcement learning.
Great. All right, Rick Lammers.
So embodied agents, and this is actually an extension of the previous question, I think. Embodied agents are often trained on reinforcement learning. Reinforcement learning has the challenge of sample efficiency, so it can take a very long time to converge. One could argue humans bring many useful priors due to the structure in their brain at birth. So when you're born with a brain, and there's some evidence that brains bring a lot of useful priors to accelerate the learning process from the scientist in a crib perspective. Do you have any thoughts on how to use pre-training and foundational models as a way to improve sample efficiency in reinforcement learning?
That's a very technical question. I like it. Yeah, so let me quickly explain a little bit. Sample efficiency means kind of how much data is needed for reinforcement learning agent to get to a certain performance. And the data here is generated by the agent itself because it's interacting. It's embodying a world, interacting and collecting data in this way. So that's what sample efficiency means. And yes, reinforcement learning is notoriously bad for its sample efficiency. Just to give some perspective, back in like 2019, OpenAI trained something called OpenAI 5 that plays Dota at world champion level, and almost concurrently DeepMind made an agent called AlphaStar that plays StarCraft at world champion level. And those things are just massively sample inefficient. You need to train them for like many months. Basically, you train them for like thousands, if not tens of thousands of years of experience, and then they can match the humans, right? But humans obviously don't have 10,000 lifetimes. So that is a problem in these algorithms. I think reinforcement learning should only be used for fine tuning. And here, I want to invoke like a mental image. Basically, Yanli Kun, Turing Award laureate, he proposed something called the Lee cake, using his name, very clever, Lee cake. So it is a cake, just a regular cake, but he put labels on it. So basically the body of the cake is unsupervised learning, and the frosting of the cake is supervised learning, and there's a cherry on top, and that is reinforcement learning. So the unsupervised learning does most of the work. This term literally means this learning goes without supervision, without human manual annotations. And supervised learning is the frosting. So that is where you have like human labels, and you use human labels to supervise the agent. And then reinforcement learning is like self-generated, interacting with the world, etc. And ChatGPT is trained this way. So ChatGPT does most of the computation in unsupervised learning because it just predicts the next word. And you don't need a human to predict the next word. It's already there in the data. And supervised learning is supervised fine-tuning. So they hire humans to write data sets. Given this instruction, this is the appropriate response, and you fine-tune on top of that. And then you do reinforcement learning. So you have the model self-generate and then use human feedback as kind of a reward signal. And I believe that's the same paradigm going into embodied agents. We should do a lot of unsupervised learning. And this unsupervised learning can come from videos, come from text, come from pre-trained language models or pre-trained multimodal models, for example. And then you do supervised learning, which is some kind of imitation learning. So let's say for robotics, we'll have a human teleoperate. You teleoperate a robot to do certain things, you collect that data, and you fine-tune on top of that. And the final step is reinforcement learning. Just set the agent free in the wild, have it interact with the world, do experimentation, be curious, basically all the fun stuff. So the AI will start to have fun at the stage of the cherry on the cake.
All right, we'll get through a few more.
Thank you. It's been wonderful listening to you. What's something that people aren't thinking about enough that you wish more people were thinking about or working on? Yeah, either a problem or a possibility. Like what's something like that hasn't gotten enough attention?
I think actually embodied agent is not getting enough attention. That's why I'm talking about and advocating for it, because I feel most of the so if we think about kind of all of the world's compute, right, like GPU compute for AI, I think maybe 99% of them are dedicated towards language models right now. And definitely much less than 1% is dedicated to agents, embodiment, all of that. And in terms of this percentage, I think the research field should dedicate more time towards that 1%. So because I feel that 1% will actually bridge the gap towards like higher levels of intelligence. So that is one thing. And the other thing that we are starting to do, but not doing enough as an entire industry, is simulation. Because embodied agents need a world to be embodied in. And of course, you can do physical robots and set them free in physical world, but that could be dangerous, right? Like if when they're doing exploration, they could hurt themselves, they could even worse hurt people around them in the physical world. And also it's extremely slow, right? Like you just think about kind of how slow those robots are moving. It's gonna take forever for them to learn anything interesting. A much better way to train embodied agents is on simulation. And the simulations, it cannot be any simulation, right? It needs to be simulations with, like, let's say photorealism, or with very complex things you can do. Like it should be open-ended simulation, supporting infinite things that you can do, and also be very, very fast. So here, I'll quickly mention like one effort at NVIDIA that I am relying on for some of my research efforts. Before being an AI company, NVIDIA was a graphics company. So actually graphics and simulation is very dear to the company. And NVIDIA has this project called Isaac Sim, Isaac as in Isaac Newton, Isaac Sim. So this is a GPU accelerated simulation engine. So you can basically parallelize 10,000 environments on a single GPU at the same time, which means you can accelerate reality 10,000 times. And in this way, you can massively scale up the amount of data exploration that a curious agent can do. And now moving back to the question about sample efficiency, this is actually another way to solve sample efficiency, is to just make sample generation speed very, very fast. That is one way to solve it. Because if you can accelerate reality at 10,000 times, you can iterate a lot more, you have a lot more data to work with, and you can experiment a lot more, and the agent can experiment a lot more. So I think this is a very promising direction moving to the future, having these extremely accelerated simulation, and also having like photorealism, GPU accelerated ray tracing, all of that. So the agent can have realistic vision systems developed in the simulations. So I believe the community should spend more time and pay more attention to simulations and embodied agents.
All right, we'll do two last questions.
Thank you for the wonderful panel, and also congratulations for the fundraise.
Unicorn.
Whoa!
Don't use that word.
Yeah, I have a very related question to the previous answer, which is, 3 years from now, 2 years from now, what's your vision in terms of how do you scale up embodied agents into, let's say, internet world, like the where most of the commerce, most of the human activity today lives in? Thanks.
Yeah, so then I think that would be like digital agents because it's not embodied anymore, right? The internet, it's more like, so are you talking about, let's say, keyboard and mouse control, something like that, to be like the internet agent? Yeah, so I think many of the principles I mentioned still apply, right? Having this Lee cake, you first do unsupervised learning, you do a bit of supervised learning, and finally have a little bit of reinforcement learning on top. But one danger is if you set the agent free on the internet, again, there are safety issues. It might do things that are dangerous, that might be illegal. I don't know, it's possible. So we need to put like guardrails around it. Just like having like a physical robot exploring in the physical space, you gotta have these guardrails. But otherwise, I think many of these principles apply. And regarding kind of interacting with the humans, right, on the internet, I think it is an interesting topic. I have not seen like an AI agent kind of interacting with humans at scale, but I would imagine there could be some like emergent behaviors, and not just on the agent side, but also on the human side, right? If the human knows, so basically, when we are prompting ChatGPT, ChatGPT is also prompting us, right? When ChatGPT first came out, we saw a lot of very creative prompts on Twitter, shared on Twitter, on Reddit. I think ChatGPT also kind of sparked our human creativity in some ways. And I do think having, internet agents interacting with humans will induce interesting emergent behaviors on both sides.
Got it. All right, one last question. How do you personally decide what's important in present and future ML research? How do you decide what's signal and what's noise on Twitter and elsewhere?
I'll talk about kind of how I decide, let's say, my own research agenda. So I have been through PhD, and PhD is extremely painful. A lot of pain and suffering. It doesn't matter where you do it, it's just pain and suffering. PhD, by the way, stands for permanent head damage. And I think, through this pain and suffering, yes, over the 5 years of PhD, I learned a lot about engineering and actual like research skills and all of that, right? You learn that. But I don't think that is the most important thing that I took away from a PhD. I think the most important thing is what we call research taste. Basically, you not only learn how to do things, but also learn how to pick what are the things worth doing. And I think the what is actually harder than the how. And that's why, being a CEO is sometimes harder than being an engineer. You need to decide, right, what to do next. You need to prioritize. And that takes a lot of experience. And it's really hard to learn from a textbook and things because everyone's different. You need to go through this pain and suffering to get there. Now, I think in AI, my research taste, because of all the kind of events I happened to be in, like, working with Dario at Baidu, working at OpenAI, seeing like scaling up, also simulation, NVIDIA simulation scaling up. Going through all of this, my research taste is towards simple and elegant solutions. And that is actually not at all obvious, at least not during my PhD time. So when I was doing PhD, I myself wrote papers, and also I've seen lots of others, my peers, writing papers that are very complicated. You have like 20 modules, for example, 20 modules interacting to deliver a solution to a very specific problem. And the reason we do this is because you can get like a higher number on a benchmark. And peer review in academia is all about, mostly about like benchmarking. Like, have you beaten the prior method by like 1% of accuracy on ImageNet benchmark or segmentation benchmark, right? So we reach for complexity as the first instinct. And it took me a very long time to unlearn that and to develop a research taste towards simple things and elegant things. And I think I took a lot from, one is from Fei, and also the other is from like observing how OpenAI builds their systems. So I still remember very clearly, when the day when Clip and DALL-E came out first, DALL-E 1 and Clip. So OpenAI released 2 models on that day. And Clip is a vision language model that learns the association between a language and the image. And DALL-E is generating image from the language, right? And they dropped both models on the same day. And that day changed the entire research field of vision language models. So vision language models as a field was extremely complicated. Like extremely complicated methods dominate the field. You got to go through complex language encoders and you segment the image in different ways and language and image interact, right? Just think about how many kind of points, right, around which you can design things. And each point can make you a PhD career. Basically, you can have PhD careers on every point of this vision language system. But what OpenAI did was extremely elegant, right? Let's say DALL-E. You just have lots of internet text and image, and you tokenize the image, and you make text and image a big fat sequence, and you predict the next token. It's so simple and so elegant, it blew my mind. I was like, wow, you can do vision language systems in this way. I did not believe it, but it works so well, and you just scale it up. And also, what's about simple and elegant solution is that they're scalable, because you don't need a lot of engineering. Well, you need engineering, but you don't need a lot of kind of pipelines and complex things. Basically, you feed it a lot of data, and all the data you can find on the internet are compatible with this simple and expressive interface. Texting image out, texting image tokens out, right? Everything can be expressing that. You don't need specific pipelines for specific types of images. So this is just one example of how I developed my research taste towards that. And today I'm still pursuing the same thing. Can we have, let's say someday, a single agent, and I'm calling that foundation agent, that can generalize to different skills, different tasks, and even different realities. So be it games or robotics is in the physical world. I don't design specific methods for this particular game, for this particular physical world and task. I don't design modules for that. I just have a single big fat transformer or whatever, just one pipeline that works across realities. And then basically every task and every agent is just different prompts to the same foundation agent. That is what I'm working towards. And I think I got that research taste from the pain and suffering, but it guides me towards building these elegant systems.
Amazing. All right. Well, on that note, huge round of applause towards Xin.